Season's greeting from Total Output Power Solutions. Dear friends, in this video we are discussing about the performance of cooling towers in thermal power plants. I am Manohar Tatvavadi from Balewadi, Pune. The cooling tower system is something like this. This is an induced draft cooling tower. You have a fan there and you have the plant heat exchanger or the condenser from where the hot water is discharged into the discharge pipes over the cooling tower. Then as it falls on the louvers below that, it is broken into the droplets and they release air, the hot air, and then the hot air is taken from the outside, the suction of the cooling tower, and the cold water is collected at the bottom of the cooling tower. This cold water is again circulated to the heat exchanger, and again this is like a closed circuit. Then if you have some makeup because of some evaporation and all this, the makeup is taken from the reservoir where there is a makeup water pump and the makeup is given to the cooling tower. So this is how the system is. Now here actually we are monitoring the cooling tower performance. So what is the importance of that? Why we want to monitor the cooling tower performance? The cooling water system, it plays a vital role in dissipation of waste heat in power station. It is actually a waste heat because the steam is not more useful. More than 60% of the total heat input to the plant is finally dissipated as waste heat. The waste heat from the power plant is carried away by circulating water and ultimately gets dissipated in cooling tower. The efficiency of the cooling tower has direct effect on condenser vacuum and in turn the heat rate of the station. 1 degree centigrade rise in cold water temperature in a 200 megawatt unit corresponds to 5 mm of vacuum loss, which corresponds to around 45 lakhs of rupees per annum in terms of direct fuel cost. Now we see the causes for performance deterioration of the cooling tower. The common causes are recirculation of vapors. You see a cooling tower there. The vapors are again being recirculated in the cooling tower, and that is what it means. Then poor airflow due to less blade angle, algae or deposition on the blades. You can see there is a blade and there is an algae deposition, so because of that the performance will deteriorate. Higher blade tip clearance. Then fan door sealing not proper. Other opening in the suction of the fan. Then damaged drip eliminator, it will cause more makeup. The choking of the nozzles may be one of the problems. Falling of nozzles may fall. Then hot water distribution, pipe leaking, breaking, or in the end, or the ends may be leaking or breaking. End covers, they may be falling. Then fill clogging. There are fills and they may have got clogged. There are damage of fills. Fills have damaged, maybe they are not there they are not there. Then lot of trees, plants, bushes, they have grown near the cooling tower. So they will restrict the airflow to some extent. Overflow of cold water basin. Unequal water flow in different cells. Improper quality of water. Then rain or any other water entering in the cooling tower. All these causes more or less point to the fact that the approach is being deteriorated from the design. The cooling tower thermal performance testing. Now how we test the performance of cooling tower? We measure the parameters. The parameters are wet bulb temperature at the tower inlet, then cold water temperature at the tower outlet, hot water temperature at tower inlet, CW flow, cooling water flow to each tower, and the fan motor power. The salient terms those are used in cooling tower performance testing are: approach is the difference between the cold water temperature at CT outlet and the inlet wet bulb temperature. You can see in the graph all the difference between the range is the difference between the hot water temperature that is inlet to CT, and cold water temperature is outlet of CT. So the effectiveness of cooling tower is 100 into HWT minus CWT divided by HWT minus WVT. This is the effectiveness of cooling tower. These are best described in the figure that is there. The salient terms which are used in cooling tower testing is the tower capability. The most reliable means to assess the cooling tower terminal thermal performance. It is defined as the percentage of water that the tower can cool to the designed cold water temperature when the inlet bulb cooling range, water flow rate, and fan motor power all are all at their design value. That is known as the tower capability. Now the salient terms used in, again, some more terms. Tower capability, as we have seen last. So here you can get the formulas for that. Adjusted test tower capability in percentage would be the adjusted test flow rate divided by the predicted water flow rate. The adjusted test flow rate will be equal to the measured flow into design of kW and test kW of fans raised to 0.333. So the predicted water flow rate will be calculated from the design approach, design flow, and actual test condition flow. Now the case study, we take a case study, design and test data, the description, unit, design, and the cooling tower 5A. You can see here the flow measured meter cube, design was 30,000, and the test measured was 30,977. Hot water temperature is 43 degrees centigrade design. Actually, it is 46 degrees centigrade in test. Cold water temperature is again 32 degrees centigrade temperature design, and actually it is 35.9 degrees centigrade. Wet bulb temperature, it was designed for 28 degrees centigrade, whereas the wet bulb temperature is 25.7 degrees centigrade. The fan power kW is designed for 65 kW, and it is taking only 47.2 kW. Now we calculate the approach for this. The approach, as already we have discussed, the design was 4 degrees centigrade, whereas in the test run it is 10.2 degrees centigrade. The range that we have calculated here, it is 11, and for design, and in the test it is 10.1, slightly less than that. So effectiveness, the percentage effectiveness, in case of design the effectiveness is 73.33, and whereas in the test run it is 49.75. The capability, you can say, if you calculate, it is the design is 100%, we take it, so based on that it comes to only 45% in the test case. The test setup for wet bulb temperature measurement, here you can see the location of inlet well bulb temperature for station with counterflow tower. This was for the counterflow tower. The L, that has to be 1.5 meters only, and X is the measurement station. Here you can measure the X is there. So it is done on both sides of the tower at air inlet path using psychrometers. The instrument shall be located within 1.5 meter of the air intake. The number of stations for the inlet wet bulb temperature measurement depends on the size and layout of the cooling tower. For a typical 500 megawatt unit having 2 cooling towers, there can be 16 locations per cooling tower, 8 on each side, for an accurate measurement of wet bulb temperature. Then comes the wet bulb temperature for station with cross flow tower. So it is depicted in the figure as well, and there is a photograph telling you about the location. So the location should be 1.5 meters, and X is the measurement station where you can measure, and here you can see one of the thermocouple which is measuring the temperature is shown there in the photograph. The cold water temperature measurement. The cold water temperature measurement can be measured directly at the point where the circulating water is discharged from the basin. The temperature measurement instrument shall be located where the water will be thoroughly mixed. It is better to have a grid arrangement in the channel for cold water measurement. In the photo you can see there is a channel and you have a grid measurement. You have got thermocouples. There are 4 thermocouples you can see, and you have provided a grid measurement, grid arrangement for the channel, and you can take the average of all these and then you can get the cold water temperature. Then the flow measurement, we have used a pitot tube for that, for flow measurement. Pitot traverse is done in 2 planes, that is vertical and horizontal, at 90 degrees to each other. The CW flow Q is equal to the dp raised to 0.5 multiplied by 504.4883 into C into A tons per hour, where Q is the CW flow, dp is the average dp measured in mmWCL, C is the pitot coefficient, and A is the area of duct in square meters. By the side you can see the duct and therein the setup for the CW flow measurement. These readings can be like this. The reading number 1, 2, 3, 4, like that. 20 readings will be taken with a certain diameter. Every time the diameter is increasing, and up to 1 meter we can take. And the location you can write there. The dp, what is the dp reading you can calculate. Dp reading you can get, and the root of dp that can be placed on the last column, and the average of the root of dp that will be taken for the equation that we have seen in the last slide. Now temperature setup for water and fan power measurement. Hot water temperature measurement will be at the tower risers or at the discharge of the inlet risers in degrees centigrade. There are risers, so there you can provide thermocouples for measurement of hot water and measure hot water temperature. The fan power measurement can be done at the individual fan switchgear. There you can get the fan power. Now the calculations. We have a table wherein approach was there. So design approach, how we have calculated. Approach is equal to cold water temperature at CT out and minus the wet bulb temperature at CT inlet. As per design, it comes out to be 4 degrees centigrade. In the test, it is coming out to be 10.2 degrees centigrade. Range. In case of range, the range is equal to hot water temperature at CT inlet minus the cold water temperature at cold water temperature. So in the design it is 11 and in the test it comes out to be 10.1. So design tower effectiveness, the design tower effectiveness comes out to be 73.33, whereas test tower effectiveness comes out to be only 49.75. The predicted CW flow, this we have to calculate. Some information is there. Cooling tower is designed for a certain CW flow, certain range and approach. For a certain designed CW flow and approach, predicted CW flow, cooling water flow, can be calculated. The predicted CW flow for a design approach would be equal to the approach test condition multiplied by design CW flow and divided by design approach. So that comes out to be, in the test condition, it comes out to be the 76,500 meter cube per hour. This is the predicted CW flow. Now we can calculate the cooling tower capability also, wherein the equation is there, cooling tower capability. The tower capability is QT by Q predicted into cell D design divided by cell T into PD divided by PT. So all the nomenclatures are there mentioned, and when if you calculate, the tower capability comes out to be around 45%. So this is the cooling tower capability. The cooling duty, evaporation losses, and blowdown and makeup water requirement are discussed here. The cooling duty handled will be equal to flow into the temperature rise. So that is equal to, it comes out to be 3,12,867.7 into 10 to the power 3 kilocalories per hour. The drift loss is 3 point. The drift loss is 0.01. It is given by the manufacturer only, and that we have calculated. The drift eliminators are in service and they are better doing. So we calculate it directly. So 0.01 into the circulation rate, whatever is the circulation rate in meter cube per hour divided by 100, that would give you 3.0977 meter cube per hour. The evaporation losses in meter cube per hour, they come out to be, now this is also a formula which has been 0.0085. The loss has been given by the evaporation loss is given by this formula, 0.00085 into 1.8 into the circulation rate into the range. So that comes out to be around 478.6 meter cube per hour. The percent evaporation loss is 1.5453. This is the evaporation loss, percentage evaporation loss. The blowdown requirement for a COC. Now the cycles of concentration or COC is of the order of 2.7 for this particular system, and so the blowdown requirement comes out to be around 281.580 meter cube per hour. So the makeup water requirement would be the total of these three, and that would come out to be 763.364 meter cube per hour. This is the makeup water that is required. Then the observations, as we have tested all this. So the observations, the fan power is less. Some fans are out or not in service, or they are under maintenance. CW temperature out is on a higher side. This may create problems in the cooling systems in the plants. The cooling range is okay. The ambient temperature may be on the higher side than design. The cooling towers are designed for a particular ambient temperature, but here the ambient temperature seems to be more, and that is why there are some problems. The range is okay. The predicted flow is much higher than the actual flow because the approach is more. Here we see that the approach is more, and that is why the predicted flow is much more higher. The wet bulb temperature shows that there is humidity in the air, which may be because of lot of trees, plants or bushes growth near the cooling tower. So they are required to be maintained clean, the clean of trees, plants and bushes just near the tower they may be there. Then the drift eliminators, they seem to be in good shape because you have the range and the is correct range. The cleaning of, now optimizing cooler tower performance, how we should do that. Cleaning of cold water basin during overhauls. Quarterly cleaning of nozzles. Visual inspection of pipes, nozzles, fills, etc. for proper water distribution. Checking of fan pitch angle, fan blade tip clearance, fan seal disc cover at the hub. Annual cleaning of fills with water jets and cleaning it manually by removing from tower when choking is more. Maintaining the quality of makeup water. Cleaning of civil structure annually and removal of algae from drift eliminators fills. Sometimes even fan blades are also with algae, so that also may be removed. Fan door and any other air ingress points to be sealed. Regular condition monitoring of CT fan should be done. Continuous chlorine dosing to be done. Slush disposal pump to be run once in a day, minimum for 15 minutes. Monthly checking of effectiveness of tower for comparison purpose, and once checking of performance during the monsoon season. So, thanks for watching. Please comment, like, share and subscribe. This Total Output Power Solutions I'm Manohar Tatwadi taking your leave. Thanks for watching once again.